Thank you. Welcome to Science on Tap. This is the inaugural show, and I hope there'll be many more. Matter of fact, I think there's going to be one more in about a month. So you'll hear all about that. I'm having a beer tonight with Chang Kee Jung, who is a professor of physics at the Stony Brook Department of Physics and Astronomy. But more to the point about this evening, he's someone who, when he watches sports, when he watches a great pass, a great catch, a great dunk, a great curveball, a great knuckleball, a great moment in sports that we all remember, he sees something very different than we do. He sees the same things, but also sees something very different. And what he sees are manifestations of the laws that govern just about everything in our world around us, things that we normally relate to cosmic issues. But he can see it related to the very, very real issues of sports and what happens on the playing field. So we have no better frame of reference to talk about than Sunday's amazing Super Bowl game. So I want to start out with just talking about that amazing pass, which was obviously the turning point of the game, from Eli Manning to Mario Manningham. When Manning let that ball go and it was traveling toward Manningham, it seemed like to me it was up in the air forever, and I didn't know what was going to happen. How long was it up there?
It was exactly 1.5 seconds. I lied, I just calculated, right? But before we do that, let's go Giants! Yay! Let's go Giants! Awesome. Okay. So yeah, that was about 1.5 seconds.
And the amount of time that ball stays in the air is called something.
Hang time.
Hang time.
Hang time. Right.
What is it about hang time that's important in football, among other sports?
So in hang time, defined as either ball or any object leaves the ground and then up in the air and it goes back down. That's the amount of time it took, we define as hang time. And typically in a basketball, when you watch Michael Jordan, or these days the new kid on the block is Blake Griffin. I don't know if you've seen him dunking about last week. It's amazing dunk. He will soar up, and it appears to be he's hung in the air and throw down the ball. In fact, the dunk he made last week is not qualified as dunk because his hand never touches the rim. He's sort of like 2-3 feet away from the basket. He jumps up. He basically throws the ball in there. But if you look at that, it looks like he's up in the air, I don't know, typically 3 seconds or 5 seconds.
One of the amazing things about Jordan was that he could be up in the air for 3 or 4 seconds.
3 or 4 seconds, right. That's what we think. But it turns out, actually it's an illusion that those basketball players, at most, they are up in the air 1 second. Actually, less than 1 second, most of them. Michael Jordan, King James, they are all about 0.9 seconds or so. And it turns out the hang time is really totally, you can calculable how fast you leave the floor, and as well as how high you jump, and the hang time. All three of them are all related to each other. If you know one thing, you can calculate everything else. All of these things can be calculated with a very simple physics 100 level of calculation. So anyway, the basketball hang time, typically all of these things we see in a slow, especially because slow motion, it looks like a forever, but it really is 1 second. That's it. And so in the football, there was, if you remember the Giants game, fantastic game that most of people doesn't talk about is punter. Giants punter, his name is Weatherford. He kicked 3 beautiful punts, and all of them landed right at around the 10-yard line. And one of them hit the ground and then went out of bounds, and so they pinned it down to 10-yard. One hit the 10-yard and got it into end zone. The other one was able, the Giants was able to stop it there.
What is the ideal hang time for a punt?
So what do you think it is now? What do you think about typical hang time of NFL players?
5 seconds?
5 seconds.
5, 6 seconds?
Actually, it's only about 4 seconds.
4 seconds.
And in fact, if you kick the ball something like as hard as 70 miles an hour, straight up, it will have the highest, longest hang time. That will be only about 6 seconds. So it's very difficult to get hang time greater than 5 seconds. Typically, if you have 5-second hang time, that's a huge, very long hang time.
Is there an ideal angle for the ball to leave your foot and travel through the air that gives you the most hang time?
That's right. So now in the kicking game, you have two purposes. One is you want to kick as far as you can, but also at the same time, you want to have a longer hang time because that allows your teammates go, tackle the guy who's catching the ball, right? So these two are actually not actually, go together. The hang time, if you want to have a longer hang time, you want to kick the ball as high angle as possible. But if you want to kick it farther, it actually turns out to be exactly about 45 degrees.
And you want the best of both worlds.
Depending on the air resistance, things like that you have to modify a little bit, but 45 degree is the one you have to kick. And so interesting thing about this angle of 45 degree throwing is that my daughter was, cross country team. That she was a field team. That she was throwing this shot put, and then I went and I saw all of the kids. They were all throwing the shot put this way because they want to throw the ball that way as fast as you can. So generally, they are throwing the ball horizontally, and what they really need to do is they need to throw up. So that's 45 degree. In fact, professional shot putters, you will think they know. But actually, if you take the average of their angles, they throw it about 38 degrees. So you really need to try to throw up higher than what you are comfortable with. So that's how it is related to 45 degree is ideal angle.
Now, hang time has a purpose.
Right.
What's the purpose of getting the maximum hang time possible?
So that is in football really. What you want is that you want to punt the ball in an exact location where you want to have. I mean, hopefully 1 yard line.
Right. As
That's
far
what
back
you
in the
far
opponent's
back and
territory
pin the other team down. But also at the same time, when the receiver gets the ball, you want to tackle and knock them down right there. You don't want to have them return. So then, let's say if I were punting the ball about 50-yard line, I'm kicking it to 1 yard. That's about 40, 50 yards you have to run. Typically, football player can run about 10 yards at 1 second. It's a good way of thinking. That's actually very fast. So if you kick it, if you have hang time of only 3 seconds, then when the other guy got the ball, your teammates are only in 20-yard line. So he has room to maneuver and run. But if you kick it such a way that you have close to 5 seconds of hang time, then as soon as he gets the ball, your teammates will knock him down. So that's why you wanted to have as much as hang time as possible.
And then you have what has become a very big issue in football, what a lot of football is about, which is getting to the opponent, tackling him.
That's right.
With great impact.
Right.
And getting him to the ground.
Right.
And that enters the physics of another very, very key aspect of football, which is the tackle, which is the contact.
Right.
And there's physics involved in that too, obviously.
Absolutely. So there are two different aspects of tackling. One is that typically the people who does not know physics, of course, coaches know empirically what is the right thing to do. But typically when you don't understand physics, you will think that best way of tackling somebody is you jump up in the air and then grab the guy and just, But actually best tackle comes from action-reaction in Newton's third law, that if you want to hit somebody strong, you need to have your feet are grounded so that you have something to lean against, push against. So that generates biggest hit. So when you want to tackle somebody, you don't jump up. You put your foot down and then hit it. And also at the same time, you want to hit the quarterback or receiver as high as you can. The reason for that is it is related with the torque. So the person is standing on the ground with the foot, and so that foot is becoming a pivoting point. And as you hit it high, and torque is not only force times the distance, what we call lever arm, from the pivot point to where the contact point is. So as that is longer, it's better. So it's easier for me to knock you down by hitting here than rather than hitting it at the belly.
Well,
so
speaking of hitting the quarterback,
Right.
I think what people in the audience may not know is that there is a hidden story about the Giants' success in the Super Bowl Sunday, which is really your tweets
that's right.
at halftime.
I tweeted it.
And could you share with all of us what happened?
Right. Well, I was a little comfortable at that when Giants were matching against, again, the Patriots, because I've seen in many years in Brady how he plays. Brady is a pretty boy. He doesn't like to be hit. He doesn't like to his jersey dirty. Sorry, yeah. But that was a little low hit. Okay, fine. But I thought really that Giants has good pass rushes. They need to really go after him. And the first half of the game, they didn't. Brady had a lot of time. He was maneuvering around. If you do that, he's going to pick you apart. So I tweeted that, gotta blitz more. Tom Coughlin, we had to blitz more. And I don't know. I mean,
It went viral.
Yeah.
It ended
Exactly.
the tweetosphere. It ended the
Retweeted it and
blogosphere.
all of that.
It got retweeted.
But second half, they're starting to get into him. And I don't know, you see him. They sacked him a couple of times. He's starting to little, kind of woozy. And so I think that got to him, I think. So that's what we won.
But getting back to hitting him,
Yeah.
hit him they did, or threaten to hit him they did, or make him
Right.
worry about being hit.
Right.
And there's good reason to worry about being hit in football.
Right. That is because concussion is a serious problem. The concussion is caused mainly because this is again related to the physics that Newton's first law, which is called law of inertia. So if we are sitting in a car, minding our own business, looking at the red light, and somebody comes and hit us, what happens to your head? It goes backward, right? The reason is that everything in that position like to stay where it is, or if it is moving, it would like to move as it is, unless it's disturbed by something. So when you're sitting here, then your head want to be here, your body want to be here, and the car, something hits behind us, the chair moves forward, but your head wanted to stay here, so that's why your head goes backward, it appeared to be. So that is Newton's first law. So concussion happens when somebody knocks you down. As you're falling down onto the ground, your skull gets stopped in the hard surface right away. But the brain inside you, the jello thingy, is still moving in that direction. And so that squashes that jello inside the brain, skull, and then detaches from skull, from part of your head. And that generates a concussion. So one way that's why we wear a helmet, right? Now, helmet does two things. One is that if you look at a helmet has inside the cushions. So what cushion does is that, imagine if, Superman movies when the big train comes and a Superman trying to stop this train before he falls off a cliff. So you have to put a lot of force. Now, if you have really, really strong force, you can stop the train right away. But if you're not, it will take a while, right? So when without the helmet, your head could be hitting the ground, concrete or whatever, right away, and that generates a huge amount of force. But if you have a cushion, that delays the amount of time, so that softened the force onto the skull. So that is one big the aspect of the helmet, the cushion in there. But another thing what it does is that there's concept of force, difference between force and pressure. Now, force is amount of total power you put into an object. The pressure is force divided by the area where the force is applied. So even though you put in a small force, but the area is very small, then because you divide it by a very small area, then that pressure gets really large.
Hammer hitting a nail.
Hammer hitting the nail. So nail has very, very, tip of the nail is very, very small. So you can hit gently with a hammer, but nail goes in because of the pressure is very, very localized, very high.
Concentrate on a little.
Right. And same thing with using knife, cutting things with a knife. Knife edge has literally no area, and that makes it, you can use small amount of force to cut things. So what helmet does is that without helmet, if I hit on the ground, then in that local area, I have very small area it's contacting, and then all the forces are concentrated in that. And that will give damage. It could actually break the skull. Imagine Muhammad Ali, who has tremendous force in his punch. He wears gloves like this. I mean, his Muhammad Ali literally has his fist is like that big with the gloves. And so when he hits somebody, that whole force is distributed in all their face. Imagine if you're hitting somebody with his just bare knuckle, and just only those 2 points is hitting, and that their face will be shattered, and one punch will shatter their face. So
Now concussions are also becoming a big issue in hockey.
yeah.
And there's a reason that, I mean, among other things, why it's particularly dangerous in hockey because of the way fights unfold.
Right. So that finishing up that the helmet thing is the helmet distributes force because of a rigid body, so the pressure is minimized, spread out. In hockey, I cringe every time when I see these hockey fighters. When they fight, hockey players fight. What they do? What do you typically see when hockey players fight? What do you see? They drop their sticks and then they take gloves off, and then they go bare knuckle fighting. So they go like this, everywhere, and every time when they hit, it's a really high pressured attack on your brain, many different spots. I forgot the name of that hockey player who died. There was a long article in the New York Times that when they examined his brain, he had many parts of the brain has dead cells, and all of these things come from that acute pressured attack on trauma on brain. So this is a serious problem in hockey. So I don't know why hockey NHL is really dealing with these things and solve the problem.
So we don't have a hockey puck on the table. We have a football, we have a softball, which we're going to get to, but we have something that is not traditionally associated with any sport.
That's correct.
Except maybe archery.
Right.
So what's this doing on the table?
Well, I would like to demonstrate the difference between force and then the concept of force and then pressure. What did I say the pressure is? What is that? What is the pressure?
Pressure is a punch, right?
Force
Force
divided by
area.
He needed some help. So if you look at this, have you ever seen people breaking an apple with one hand, splitting an apple in one hand? No. I'm not a very strong guy, but you can actually do that.
I have tried this at home, by the way, and I've gone through a lot of apples and nothing has happened.
Here, you can check this out.
Not a trick apple.
No, it's really. Try to trick.
No, just
No,
check it.
probably
Just check
will.
it. I just
We'll
want to
know.
make sure that it's not rigged. Don't eat it. Don't eat it. Okay, I'm going to try to split this apple with one hand. Hopefully it works.
Well, we know he can't do it a second time. We know he can't do it a second time. So why did that happen? Why did that happen? Incredible. And a pretty even split.
Yeah.
Thank you very much, miss.
So I'm not going to actually, this is a little bit of like what I do in my tricks in my classes and things. Sometimes things are left a little bit mysterious. It's better for the people, the students especially, to think. So I split these things by putting an acute pressure in one part of apple. And if you do it right, then it just breaks quickly. And let me just leave it at that.
Okay.
Okay.
And you'll have an
So the
opportunity to try
important
to
thing
do
is
this.
that area, right? That just
pressure
like
on the
nail or knife, sharper the knife, that means area is smaller. That's how you don't need a lot of force to cut through things. Nail need to be sharp tip, which is
Right.
small area. Same thing. If you want to If you want to
Same thing about a sharp blade, which I thought was
You have to
fascinating.
make
Sharpness.
everything sharp. You have to have small area.
Which is the minimum.
Yeah.
All right, well, we have, as I said, we have a football, we have a baseball, a softball, a baseball back here. They have a lot in common. The ways they go through the air, how they're thrown, why they're thrown the way they throw, and what makes a great pass, what makes a great pitch. And we're going to find out about all that when we come back in about 5 minutes. So thank you very much.
Great.